Hello and welcome to this video about doing math on a computer. In this video we'll learn how to get the nth antiderivative of the logarithm of x. It's not that straightforward. We'd need to have a table of all the antiderivatives of log x from 1 to n, and this would need to be calculated by a computer. This computer program could store values going up to the 100th antiderivative or even larger. So we'll start with getting the derivatives of log x. We'll write it out as the natural logarithm function, ln x, to give this function more certainty that we're working with the natural logarithm, rather than the logarithm of 10 or 2. This is the derivative of log x. I didn't write the whole calculation out because I'm assuming that it's true in this video. We can then very easily find a second derivative, and using indice notation, we can very easily find the nth derivative of log x. So now to work in the opposite direction. What would the integral of y with respect to x be? That is, what is the antiderivative of log x? We can use indice notation to write it out like this, and we can then ignore the constants, because we can always put them in later if we want to make exact calculations for upper and lower bounds. And then we can ask what is the nth antiderivative of log x, written like this. So I'll assume that we already know the answer and show that it is true. We'll set w to be the answer. Then we'll get the first derivative of w using the product rule. And we'll quickly go through all of the calculations to show that this expression is the first antiderivative of log x. And so we can write it out more formally that this is the first derivative of log x. It has two terms added together. It doesn't look much more complicated. So now I'll make a claim that the nth antiderivative of log x is of this form, which is fairly simple to store in a computer. And now I'll start to prove it. If we take the derivative of an expression of the same form, then it should give an expression of this form too. And so we can work backwards and thus show that this claim is correct. So we'll take the first derivative of this expression using the product rule and the exponent rule for x. Then we'll manipulate this expression using the rules of calculus. Then we'll simplify it to be this expression, which is in the most simplified form. And then this expression can be manipulated to be in the form shown above in the claim. So we've proven this claim enough, since any two numbers can be expressed as these two constants a and b like this. So now we can manipulate these equations so that we can get the next values of a and b from the last ones. We'll firstly get these equations, and then we can combine them to give us these equations. This is the first pair of constants in terms of the next pair. We can rearrange them so that these constants are the subjects of these equations. So this is how to calculate the next constants from the previous constants that give us the next antiderivative. And we can rewrite them like this. So these equations give us the next pair of constants to give us the next antiderivative of log x from the previous antiderivative. And we can use these equations to keep finding all of the antiderivatives of log x up to the nth antiderivative. So let's use these equations to get the next few antiderivatives of log x. We can write out log x like this so as to show us what the values of the constants are. And so we'll write down the actual value of these constants. Then we'll use the equations that we've just found to find the values of the next constants. Firstly, we'll find the next value of a. Then we'll find the next value of b, which is more complicated. And then we can use these constants to find the next constants for the second antiderivative. We'll find a first. And then we'll find b. So we've found the first two antiderivatives of log x. So this is the data structure that we'll be storing this list of antiderivatives in. We'll only need two constants for each antiderivative, and they'll be stored as pairs of entries next to each other in an array called log table. They'll be accessed this way. ai will be accessed from this array by multiplying I by 2, and then using this number to access the array. And bi would be the number next to it, which would be I times 2 plus 1, and the number of functions stored in this array would be stored in n log. So now to construct the computer program to find all of these constants, which can be used to construct all of the next n antiderivatives of log x. We'll store all of these values in an array called log table, and we'll store them as numbers next to each other in the same array. We'll store the initial constants here, which represent log x. We'll make a loop to get all of the constants for the next n antiderivatives of log x. So we'll get the last calculated constants from the table, or they may be the first constants that we've plugged in. We'll get the value of I plus 1 and set another variable j equal to it to conserve memory and make the function run faster. Then we'll get the next constants using the formula that we derived earlier. Then we'll put these values into the table in the next position. Then we'll set the size of the table or number of pairs of constants in the table equal to this value. Now to write up a function to test whether or not this table is correct. We'll firstly print out a message that this function has been started. We're testing the ith entry in this table, so we'll print out error messages if I isn't in range. We'll make up a loop to test this particular entry n1 times. n1 can be set to anything. It's set to 2 to begin with and 1000 at the end. We'll get a good selection of numbers to test. We'll use R for random. We'll get values that are a tiny number epsilon larger and smaller than it. And we'll get the natural logarithms of all of these numbers. We'll get all of the constants from the array for the ith and I plus 1 constants. We'll start to calculate the values of the function here. And we'll start to calculate the values of the second function that we're testing it against here. So this is the value of the ith antiderivative of log x. And this is the derivative of the I plus 1 antiderivative of log x. We're using numerical differentiation to find its derivative here, and it should be very close to the value of the ith derivative. And so we'll get the difference between these two values, both the relative and absolute difference, and choose the smallest one. And if the difference between them isn't small enough, then we'll print out an error message and a large amount of variables, so that we can debug the program properly. You'd be free to look at any variables that you want to here. And then we'd print out a finished message when we're done. And this is the function that we'd use to put all of the testing together. We'd firstly make up the table. We've made it up to the first 12 antiderivatives, and we'd print it out using this function. Then we'd test each entry from 1 to 11 and test it 1000 times, and it does go surprisingly quickly. So this is the function to print out the table in terms of algebra that we'd be able to read. We'll write it out with the third biggest heading. Then we'd make a loop to go through the entire table. Then we'd get the constants for the antiderivative here. We'd write out the ith antiderivative of y here. Then we'd calculate the expression in algebraic form here, obeying the rules of algebra. I'll store it in this string str. I won't go into it here. We'd write out this expression here. Then we'd write out carriage returns here. And this is the function to write out the constants as they are stored in the array. This function is fairly straightforward. And so this is the printout of the table showing the first 12 antiderivatives of log x. The function always remains simple, but the constants get smaller and much more complicated. I can't think of any uses for it, except that it shows that the nth antiderivative of log x can easily be found. So I hope that you have found this video to be helpful, insightful, educational, and maybe even interesting. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video, and thanks a lot for watching.